This is Unit 4, Chapter 15, Section 15.6, Triple Integrals. So we have defined single integrals for functions of one variable and double integrals for functions of two variables. So we can define triple integrals for functions of three variables. So we're going to first deal with the simplest case, where f is defined on a rectangular box as shown in equation 1. The first step is to divide b into subboxes, and we do this by dividing the interval a sub b into I intervals of equal width delta x, dividing c and d into m subintervals of width delta y, and dividing rs into n subintervals of width delta z. The planes through the endpoints of these subintervals are parallel to the coordinate planes, and they divide the box B into subboxes, which are shown in Figure 1. Each subbox is going to have a volume of delta V is delta X, delta Y, and delta Z. We then form the triple Riemann sum as shown in equation 2, where the sample point is inside of each of these one of these boxes. By analogy with the definition of a double integral, we can define the triple integral as the limit of the triple Riemann sums shown in equation 2. And then the triple integral of f over the box B is given as equation 3, provided that the limit exists. And again, the triple integral always exists if f is continuous. We can choose the sample point to be any point in the subbox, but if we choose it to be the point x sub I, y sub j, z sub k, we get the expression as shown in equation 3. Just as for double integrals, the practical method for evaluating triple integrals is to express them as iterated integrals, as shown at the end of equation 3. And again, Fubini's theorem for triple integrals, if f is continuous on the rectangular box, then we have the triple integral of f of x, y, and z dv is going to be defined as the integral from r to s, c to d, and a to b of our function f of x, y, z, dx, dy, dz. The iterated integral on the right side of Fubini's theorem means we integrate first with respect to x, then we integrate with respect to y, and finally we integrate with respect to z. There are 5 other possible orders in which we can integrate, all of which will give the same value. So let's go ahead and take a look at example 1, and we have the triple integral x, y, z squared over the rectangular box B, where b is defined as x from 0 to 1, y from -1 to 2, and z from 0 to 3. We could use any of the 6 possible orders of integration. If we chose to integrate with respect to x, y, and then z, we then would have that the triple integral over b of x, y, z squared dv is equal to the interval from 0 to 3, -1 to 2, 0 to 1, x, y, z squared, dx, dy, dz. Now, we notice that because this is fully factorable and the limits of integration are numbers as opposed to functions, we can rewrite this as the integral from 0 to 3 of z squared dz, -1 to 2 of y dy, and 0 to 1 of x dx. And as we evaluate this, we're going to end up with the value of 27 over 4. So now we're going to define the triple integral over a general bounded region E in 3-dimensional space, or a solid, by much the same procedure we use for double integrals. We're going to enclose our region E in a box of the type given by equation 1. Then we're going to define f so that it agrees with, define our capital F so that it agrees with our original function on E, but is 0 for points in B that are outside of E. And then this integral will exist if our lowercase f is continuous and the boundary of E is reasonably smooth. The triple integral has essentially the same properties as the double integral. And we're going to restrict our attention to continuous functions f and to simple types of regions. So a solid region is said to be of type 1 if it lies between the graphs of two continuous functions of x and y, as shown in equation 5. Then we can define our triple integral over the region E as the double integral over region D of the single integral evaluated from u sub 1 of xy to u sub 2 of xy of our function The meaning of the inner integral on the right side of equation 6 is that x and y are held fixed, and therefore u sub 1 of xy and u sub 2 of xy are regarded as constants, while our function is integrated with respect to z. Now, if we were to have region D as a type 1 plane region, as we recall from double integrals, then our triple integral would become the integral from a to b and g sub 1 of x to g sub 2 of x our function f of x, y, z, integrate with respect to z, and then y, and then x. If we were to have our region D as a type 2 plane region from our study of double integrals, then our integral would be from c to d, h1 of y to h2 of y, and again the u1 of xy to u2 of xy, f of x, y, z, integrate with respect to z, then x, and then y. So this is a type 1 plane region or a type 2 plane region. A solid region is of type 2 if it's of the form as shown, where at this time D is the projection of E onto the YZ plane. The back surface is going to be x is equal to u sub 1 of yz, and the front surface is x is equal to u sub 2 of yz. And then we would have the triple integral over the region E of our function f of x, y, z dv is going to be the double integral over the region D u sub 1 of yz to u sub 2 of yz of our function f of x, y, z. Again, we're going to integrate this time with respect to x first. And then dA. And then finally, we will have a type 3 region where D is the projection of E onto the xz plane. Y is equal to u sub 1 of xz is the left surface, and y equals u sub 2 of xz is the right surface as shown in figure 8. And then we have our triple integral as defined as follows, where it's going to be the double integral over our region D, the integral from u sub 1 of xz to u sub 2 of xz of our function f of x, y, z, integrate with respect to y first, and then dA. Now, in each of these equations, there may be two possible expressions for the integral, depending on whether our region D is a type 1 or a type 2 plane region, which corresponds to what we saw with the type 1 solid regions. So moving on to some applications of triple integrals. We know that if our function is greater than or equal to 0, then the single integral represents the area under the curve from a to b. And if a function of two variables is greater than or equal to 0, then the double integral over region D dA represents the volume under the surface and above D. The corresponding interpretation of the triple integral over the solid region E, where the function is greater than or equal to 0, is not very useful because it would be the hypervolume of a four-dimensional object. And of course, that is very difficult to visualize. And remember that E is just the domain of the function f. The graph of f is going to end up lying in a four-dimensional space. Nonetheless, the triple integral over the region E of a function of three variables can be interpreted in different ways in different physical situations, depending on the physical interpretations of x, y, and z and our function of x, y, and z. So beginning with the special case where f of x, y, z equals to 1 for all points in E, then the triple integral does indeed represent the volume of our solid region E. For example, you can see this in the case of a type 1 region by putting f of x, y, z into formula 6. And so we would then have the triple integral over region E of 1 dv would be the double integral over the region D and the integral from u sub 2 of xy of 1 dz times dA is then going to be the double integral over the region D of u sub 2 of xy minus u sub 1 of xy dA. And we know that this represents the volume that lies between the surfaces z equals u sub 1 of xy and z equals u sub 2 of xy. So we're going to use a triple integral to find the volume of the tetrahedron T bounded by the planes x plus 2y plus z equals 2, x equals 2y, x equals 0, and z equals 0. So the tetrahedron is shown in figure 14, and its projection on the xy plane is shown in figure 15. So the lower boundary of the tetrahedron is the plane z equals 0, and the upper boundary is the plane x plus 2y plus z equals 2, or then z equals 2 minus x minus 2y. So therefore, we have the volume of the tetrahedron is going to be the triple integral over the region T dv, which is then going to be the integral from 0 to 1. We're going to go from x over 2 up to 1 minus x over 2, from 0 to 2 minus x minus 2y of 1 dz dy and then dx. So I'm going to leave this calculation to you in the video and to determine the volume as given.